We finished off the divisibility rules, and I guess we did talk a little bit about least common multiples and greatest common divisors, and talked about how our idea of prime factorization would help us to see what the answers are and what that's talking about. And we sort of talked about what skip counting and jumping and hitting the same tiles and not hitting the same tiles, sort of that idea of least common multiples and greatest common divisors. But yeah, we have discussed everything out of chapter 4 at this point. That being said, like if we've discussed everything out of chapter 4, what does that probably mean? It probably means there's a test coming up soon, right? Well, I'm gonna wait till everybody gets here. Yes, I was leading into that, right? It's like, well, I mean, it looks like we've accumulated enough knowledge to have a test over it. Okay, we will officially start and we'll officially answer your question. So we've covered everything out of chapter 3 and out of chapter 4. Now, some of the chapter 3 stuff was on the previous test, but all of the stuff involving sort of the addition and subtraction and multiplication and division that we did in a little bit more detail, right? All of that, along with the stuff out of chapter 4 here, that will make up the material for the third test. Okay. Just so we have plenty of time to think through things and work on homework problems and come to my office and ask questions and all that kind of stuff, we will make the test a week from Wednesday. Okay. Typically, I would make it a week from today, but usually Monday tests are not good. It's usually just not a good idea to have a test on Monday. So we're going to do a week from Wednesday. So obviously we're going to continue studying new material and talking about that. We're not going to have a review for a week and a half, but make sure that you have enough time to finish up problems and definitely not to give a test on a Monday, because that just is usually a bad idea. So a week from Wednesday, we will have a test. There you go, the 28th. Okay, so the 28th, we will have a test over the new stuff that we've been doing out of chapter 3 and the stuff here out of chapter 4. And that's what will be on the test. So I thought today, just as sort of a last culmination of the stuff out of chapter 4, to try to show you something that might be fun and interesting. I think it's fun and interesting. So I'm going to go there with that. You may or may not find it fun and interesting. We're actually going to look at example 4.9 out of section 4.2. And it says, working with the ISBN 13 code, right? So the ISBNs that you get on books, all right, we're going to talk about that a little bit. And then we're going to talk about other things that this is related to, all right? But let's start here. Okay, so let's look. This is going to do what? It starts at the very bottom of page 201 and will carry over into page 202. All right, so the very bottom of page 201 says, since 2007, an ISBN is a 13-digit code separated into 5 parts. In particular, the first 12 digits are divided into 4 groups that identify the type of industry, a language group, the publisher, and the specific book. The last symbol is the check digit, some digit 0 to 9. The check digit is chosen so that when the 13 digits are multiplied by the alternating factors of 1, 3, 1, 3, 1, 3, and then they are summed together, the final product, once you throw the check digit in, is a multiple of 10. It says here is an example. All right. So first, I guess before we do the example, let's think about why we might need a check digit. What would be the purpose of a check digit as they're talking about here? Well, really, it's a way to try to make sure that you don't make a typo somewhere. I mean, that's really it, right? I've got this long string of numbers, right? I want to make sure that I didn't make a typo somewhere. So this string of numbers has to have a very certain property to it, okay? And so when we take the string of numbers that's supposed to be the ISBN and we sort of run it through our test procedure, we're either going to go, yes, that was a valid ISBN, or no, it's not. Now, we could still make a mistake and somehow accidentally type in something where everything would pan out, but it was the wrong book. But more times than not, if I make a mistake with one of the digits, it's going to pick it up and say, you don't have a valid ISBN number. All right. So let's take a look, and then we'll talk a little bit more about where this stuff comes up. So here it says, here's an example of how this works. So here's the ISBN. We're going to, let's see, 978-0-321-69312-9. All right. Now, it says what we're supposed to do is we're supposed to multiply and then add. All right. So it says alternate, multiplying by 1 and then 3 and then 1 and then 3 and then 1 and then 3 and then add everything up. Okay? So let's take a look. So we're going to multiply all the way down. So we're going to see what we get. So 9 and 1 is 9. 7 and 3, 21. 8 and 1 is 8. 0 and 3 is 0. 3 and 1 is 3. 2 times 3 is 6. 1 times 1 is 1. 6 times 3, 18. 9 times 1 is 9. 3 times 3, 9. 1 times 1 is 1. 2 times 3, 6. 9 times 1 is 9. So I'm going to leave this. Now it says what we're going to do is we want to add them all up. Okay? Right now, I'm going to try to, let's think of it this way. All right? All of this information is based on the book. Okay? This is what we choose. Okay, the last digit is something that we choose. Okay? Is that all right? So we choose the last digit. All the other digits are based on information about the book. Like they said, like the language, the publisher, the title, well, like all that kind of stuff. That's what those digits are. All right? So let's think of it this way. Here's how it would play out, right? At first, you wouldn't have the 9 there, okay? So at first, I wouldn't know what was there. Okay, if I were making up an ISBN, let's say I'm making up the ISBN. Is that okay? So at first I don't know what's there. So now I've got 9 plus 21 is how much? 30 plus 8, 38, plus another 0 is 38, plus 3 is 41, plus 6 is 47, plus 1 is 48, plus 18. Is that 66? 18? Plus 9, 75. Plus 9 is 86. Plus 1 is 80. How am I doing? Oh gosh, it's not 86. Is 84. Plus 1 is 85. Plus 6 is 91. Is 91 divisible by 10? No. So what's the, moving up, because we're only adding, right? We're not subtracting. What's the next number that's divisible by 10? 100. How do we get there? Plus 9. So that's my check digit for the book. Okay? So that way, if, let's say someone made a mistake somewhere. Okay, let's see if we can point this out. So let's do this. If someone makes a mistake, oh, well, why make it too terribly difficult on ourselves? Let's say we did the last one, right? And we accidentally put a 1 there instead of a 2, right? I just typed it in wrong. Why? Because 1's right next to 2 on the keyboard, right? So I just typed the wrong number in, okay? Then down here, right, instead of a 6, I'm going to get 3, right? 1 times 3. So then when I add everything up, instead of getting 100, I'm going to get 97. And 97 is not divisible by 10. And so when I type this number in, the computer's going to sort of run it through the algorithm and say, that's not a valid ISBN number. Does this make sense? Right? So how many of you have ever ordered something online with your credit card? How many of you ever put the wrong credit card number in? How many of you ever had the computer say, this is not a valid credit card number? Because it ran through the algorithm with the check digit and it was not divisible by what it was supposed to be divisible by. So whatever you typed in was not a valid credit card number. Okay? You set up a certain algorithm. Again, all the earlier information is based on technical stuff about what you're dealing with. The last number is to just shift things, add by some number 0 to 9 so that it's divisible by what you need it to be divisible by. All right. Well, the publisher does, right? So the credit card company like sets up the first 15 digits on your credit card. The 16th digit is not information encoded about the credit card company or your account. It is a check digit to make sure that you don't make a mistake when you type all of the other numbers in. Does that make sense? And again, there could be some ways where I could type enough bad numbers in that it would still think it was okay. But for the most part, if you miss one of the numbers, you're not going to get something divisible by 10 at the end. And it's going to say you've made a mistake somewhere. Is that okay? And so this works for ISBN numbers. And this is not the only way that you would do it, right? So you would need to go, if you wanted to have the students sort of explore different ways that things like this show up, credit cards are definitely a common one where this stuff works, right? The first 15 digits encode information about sort of where you're from, All right. Was this issued in the United States, or was it issued in Canada or over in Europe or wherever? It lets you know whether or not it's a Visa card or a MasterCard or a Discover card or whatever. Okay. And then there's information about your particular account, a way to identify your account. And then the last number is a check digit, right? And so you can go through and see how does all of this work. And again, this is one example of an algorithm that's used. This is how they do it for ISBN numbers. All right. But for credit card numbers, there's a different algorithm that's used. Notice it's all based on arithmetic, though, which is really cool for the students, right? So it's a bunch of arithmetic with this added condition that I need to pick the last digit so that the divisibility is what I want. Okay. And so I can pick out my check digit and I choose it and I put it in there. And then I can also identify if a number has been entered incorrectly, right? Of course, why would I want information like this? Well, I mean, it would be really bad if what I could do is just enter in 16 random numbers and somehow that's a credit card something and I just go buy random stuff. Does that make sense? Right? So there's all kinds of sort of checks and information encoded in those 16 digits, all right, to make sure that you've entered a valid credit card number, whether it was because you were trying to be deceitful or whether it was like, oh, I accidentally just hit the wrong key when I was entering the information in, right? And again, I think many of us said we've done that at some point. I can remember that I've done it. I remember thinking it was interesting when I entered a credit card number and it was like, hey, this is a MasterCard. Do you know it was a MasterCard? I didn't tell you it was a MasterCard, right? So there's all this information that's encoded into it, right? And so this is kind of an interesting place where students see the applicability of sort of number theory and divisibility. Another place similar to this is in what we call like encryption and cryptography, right? There's a lot of number theory that's attached to how you do cryptography to encode information so that other people can't read it. All right. And so you use divisibility and prime numbers and multiples and all this kind of stuff to sort of take some information and encode it. All right. And so how it would have worked historically, this is actually a fun thing to do with kids, is to show them sort of the history of cryptography as a way to look at number theory information. Right. And so you would say, okay, this is the way that we're going to encode the information. I'm going to take this letter, this phrase, this whatever, and I'm going to change the letters into numbers in some way. I'm somehow going to encode the letters into numbers. Then what I'm going to do is I'm going to send the information to someone else, and what they have, so what they get is this sort of string of numbers, right? And so if I'm, you can think if I sort of intercept the message, the idea is that I'm going to look at it. It's just a string of numbers. And so it doesn't make any sense to me, right? Or maybe I've converted it back to letters, but now everything's all rearranged and jumbled, and so it doesn't make any sense to me. But the person that I'm sending the information to, they have sort of the mathematics behind how I encoded it, so they can decode it, right? So they get this long string of numbers, and what they have is the key. And the key says, well, this is how you encoded it. So you undo those steps and you're going to decode the message, right? So that I can send information to someone else. And the only way that someone intercepting it would be able to deal with it is if they had the key. So how are they going to get the key? Either they tortured someone who has the key or someone's a traitor, right? Does this make sense? And so this is how things would have originally been done, right? And then eventually they enough with number theory to find out a way that, like, I can encode it and you can decode it, and we never have a transaction, right? So once you get enough sort of number theory and how this stuff works under your belt, and you get a little bit more sophisticated, now you can sort of encode and decode sort of without the key that someone could intercept. All right. And so that's kind of how stuff is done now, which is called RSA encryption. That's one of the key ways that things are encoded and secured nowadays. It deals with a lot about large prime numbers and factorizations and this kind of stuff. And really the issue is, even if you wanted to try to decode it, like the computing power that it would take to decode it, like you may get the message in a few thousand years, right? And by then you wouldn't be able to do it. So like to just sort of brute force try to decode it by cycling through all the possible options, like you'd never get the information in time, right? And so cryptography and things like how you encode information into ISBN numbers and credit card numbers and those kinds of things, that's where you can bring sort of the number theory aspects into sort of the practical real world to show to the students, right? Because, I mean, maybe we like hopscotching our way to similar squares and playing around with divisibility rules, and that's all fine and good, but to really spark the students' interest, I think it's good for them to see where this stuff is actually used in the world, right? How do we use this stuff? And those are some of the main ways that it's used that I think would really spark the interest of the students. So I wanted to make sure that, one, we looked at this example, but also that we talked a little bit about sort of other avenues that you could branch out into in terms of looking at number theory and things that deal with all the kinds of interesting stuff that we can do just with arithmetic, right? I mean, we have to be we're being sophisticated with it, right? We're forcing them to think critically about it, but they're doing arithmetic proper, right? And what we would call number theory to do all of the cryptography and the sort of the checks and balances that go into these numbering systems that you see. Okay, that's where y'all all go, oh, wow, that was so cool. Thank you. All right. Anyway, so any questions or comments or thoughts about that? All right. So again, the cool thing here is that you could go through a whole sequence of stuff. You could have them check to see whether things are correct or not correct. Was there a mistake somewhere? You could have them go through and be the one who's in charge of picking out the check digit, like making the check digits, right? And so there are all these different things that you can do to sort of make this come to life with students, all the while helping them to solidify the conceptual things that you're trying to teach them. Okay, questions, comments, concerns about chapter 4? Or maybe you're like, I probably need to go work some more problems and then I'll have questions later. Okay, then we'll do that. Then we're going to just say, like, for chapter 4, now it's really up to you to go work problems, and I'll field questions here or there as they come up. We want to take a look at chapter 5. Okay, so where are we going next? So there are 3 chapters left for this particular semester. All right, 5, 6, and 7. 5 is integers, 6 is fractions, 7 is decimal numbers, okay, decimal representations, all right? So we're going to talk a little bit about sort of the natural practical development. Again, we always want to motivate everything that we learn in mathematics by how it's used. Why is it useful? All right. That's the best way to engage our students, right? Why is it useful? And it's going to be very hard to motivate our students by saying it's useful because I can do other math with it. All right. Or later on, I can do math with it, right? I need to see why it's useful now, right? Why is it useful for me today? What could I go home and play around with at my house to see the usefulness of this right now, right when I leave school? Does that make sense? And that doesn't mean that there's not usefulness outside of today or later on, right? But if you say, look, we're going to learn this because in 7 years, you're going to need to be able to do something. That's probably not very motivating, right? You're like, well, I mean, okay, maybe, right? But probably not. Like, what's the usefulness of it now? And also, what's the history of it? Right? So let's take a look. Chapter 5 says integers. If we look at the sections, it says 5.1, representations of integers, 5.2, addition and subtraction of integers, 5.3, multiplication and division of integers. right? So what are we doing? In some sense, we're going to go right back through everything that we've done for whole numbers, but we're going to look at it in the context of integers. And then we're going to do it again in the context of fractions. And then we're going to do it again in the context of decimal numbers and see how things change and how things build, right? So what I hope to give you is one, a practical usefulness and a reasonableness to the idea of integers and fractions and decimal numbers in a way that sort of the students could see right then immediately, right? And also to show you what you've possibly gained in terms of sort of the mathematical structure over what you had in just dealing with the whole numbers. All right, so those are the things that we're going to try to do. So first things first, integers. What in the world? All right. How do I motivate integers? I think that's the first question. Where do they come from? Is it natural and reasonable? Is it useful? Right? Historically, for a long time, there really weren't negative numbers in use. Eventually, they were in use, but for a long time, the whole numbers were what you had. Like it was like, well, I mean, we're just going to count up things, and that's what we have. All right. And then eventually you start to see the reasonableness and the necessity of having things like integers and fractions, and then moving on into decimal numbers. So what's one purpose of an integer? Well, I could go purely mathematical. All right. Was that me? What was that? Oh, yeah, I don't know what I was saying. All right. All right, so I could take this and say, okay, I've got a number line. All right, I've been drawing number lines with my students. All right. And then I could have a student sort of ask the question, well, what happens if I do 4 minus 5, right? And hopefully, although this has happened in the past, hopefully my teacher does not say, oh, well, that's not something that you can ever do. You can't ever do 4 minus 5, right? These things have been said before. Don't ever say that to your students, right? At worst, you can say, well, look, we're not going to discuss that type of thing now, but you'll see that when you get to such and such grade, right? Because are your students going to see this at early ages? Absolutely. They're going to just swap the order of the numbers. You want them to do 5 minus 4 and get 1, and they swapped the numbers, right? And then either one, they're going to say, well, it's always 1, and it doesn't matter which order I write it in. Well, that's an issue, right? Or, unfortunately, a teacher might say, well, you can't do that. That's an issue because that's a lie, right? You can't. You can definitely you can do it. It is a number. It does exist. It represents something, right? It may not be something you want to talk about right then, and that's fine, right? That's an appropriate response. Or, well, you're going to learn this in such and such grade. You'll do this next year. We're not going to work on that right now. Right now, we're always going to work on it this way, all right? But nonetheless, you could say, oh, well, I want to do 4 minus 5. And so you go, okay, well, so there's my 4, right? And then, of course, notice that's 5, okay? So what does 4 minus 5 look like? Well, based on our rules, that's 4 minus 5. I go 4 and then minus the 5. Is this okay? Fair enough? And of course, at least at this point, I would say, well, I don't have a number for that yet. Maybe that would be a good answer, right? Wherever this is not on the map, right? Doesn't mean that it can't be on the map. I just need to extend my map, right? I've got a truncated version of the map. I can only see this portion of the map, but there is more to the map. And so this appears to be 1 unit away, but on the other side of 0, if you will. Is that all right? Fair enough. So it's 1 over there, right? And you go, okay, well, how do I write that? Because now this is confusing because I have a 1 here and I have a 1 there. And so now next time, if you say 1, where am I? Does this make sense? Right? So you say, well, so I have a 1 here and a 1 here, and somehow I have to distinguish between the two. Which one am I going to pick? Right? And so our convention, based on addition and subtraction and how all of this stuff fits together, is to put a minus sign in front of it. And we call it -1. Okay? Now, technically, that means this is +1 or +1, right? Of course, we usually don't write the plus, right? Conventionally, we never write the plus. If it's positive, we just write the number. If it's negative, then we write the distinction. Does this make sense? Fair enough? All right. So I could do that. All right. That's perfectly fine. And I could say, okay, just mathematically, what we're going to do is we're going to extend it so that if we were going to do something like this and it sent us past 0 in the other direction, we could still do that. Right? And we say, all right, great. We're gonna make all these other things over here. Right? Is that okay? But that's not the only way that I could do it. That's not the only way that I could talk about it. Right? What are some practical ones that we experience in our daily lives? Well, I don't know that we experience this in Texas, but you would definitely experience it if you lived in colder climates. Somehow, we can have temperatures that are below 0, which seems a little weird. Doesn't happen much in Texas, but it does happen in other places. I've lived places where the temperature was below 0. Okay? So what does that mean, right? And that kind of goes into this, if I were going to think conceptually. In some sense, why do I have negative numbers? Well, at some point, I decided where my starting point was going to be, right? Where my 0 is. And when I did it, the reality was I needed things on both sides of it for stuff to work out. Is that okay? I needed stuff on both sides of it. So, for example, let's take temperature for a while. I think the easiest one is probably the Celsius scale, although it's not necessarily the one that we use in our daily lives for telling temperature here in the United States. The Celsius scale, 0 is not chosen because it's the coldest possible temperature that we can experience. Okay? 0 is chosen because when you hit that temperature, what happens? Anybody know? Water freezes. Okay? So the scale was chosen so that at 0, water freezes. And at 100, water boils. And so it was that property that decided the location of 0 and the size of 1. The size of 1 will matter in the next chapter when we talk about fractions. At some point, I have to decide this is 1. And I don't keep changing 1. This is what 1 is in my world, right? And so I have 0 and I have a 1 scale. The 1 is based on 100 being when it boils, 0 when it freezes. But it doesn't mean that you can't get colder than that. Okay, you can be colder than the freezing point of water. So somehow I have to account for that. So what do? I just keep extending my scale and putting more markings. Okay, and so you bring thermometers to class, right? And you've got this scale, and you've got 0 marked, but 0's not marked at the bottom, right? It's not the lowest possible value. The mark for 0 is for another reason, right? It's marked at 0 for a reason of a different importance than being the lowest possible temperature. One of the reasons for that is if you were to do what we would call absolute 0, you'd have gigantic numbers for our everyday temperature, right? Which is not very reasonable. Okay, it would be a mess to manage. Then you could have, you could say, well, I'm going to go look at the Fahrenheit scale, right? And this really probably needs to tie into chapter 5, but chapter 6, but we're going to talk about it here in 5 anyway. So with the Fahrenheit scale,